Have you ever stopped to think that the matter making up everything around you, from the air you breathe to the screen you're reading right now, was once an almost unsolvable mystery? The most curious part is that the answer didn't come through long, obvious explanations, but through a bold idea that seemed almost absurd at the time. What if electrons weren't free to spin however they wanted, but were instead prisoners of invisible rules? That simple yet provocative question opened the way to one of the greatest leaps in science. Niels Bohr's atomic model isn't just a theory locked in school textbooks, it's the key that helped reveal the behavior of light, matter, and even the very technologies you use today without noticing. But here's the catch. Behind this seemingly organized explanation lies a fascinating controversy, full of paradoxes and limitations that few people know about. And that's exactly where the secret lies. Understanding Bohr's model isn't just revisiting a piece of history, it's discovering how a counterintuitive idea changed the way we see the universe, and how it might just change the way you look at knowledge from now on. The beginning of this story is almost like trying to put together a puzzle without having all the pieces. Rutherford took a huge step by showing that the atom had a central nucleus, dense and positively charged. But let's be honest, the picture was still incomplete. According to him, electrons orbited around like planets circling the sun, yet there was one detail that didn't add up. If that were true, they would lose energy and eventually collapse into the nucleus, which, in practice, simply didn't happen. It was like looking at a lit bulb and not understanding why it didn't go out after a few seconds. Rutherford's theory was brilliant to explain the existence of the nucleus, but weak when it came to justifying the stability of atoms. Imagine trying to explain why a fan keeps spinning even without power. The math just doesn't work. This limitation opened the door for restless minds to search for answers beyond classical physics. And that's when the stage was set for a revolution. Science needed someone to bring a new way of seeing electrons, not just as runners on undefined tracks, but as particles obeying discrete and unexpected laws. It was as if everyone was waiting for a maestro to organize this chaotic orchestra, and that maestro would be Niels Bohr, with his postulates that would forever change the way we understand matter. Bohr came in to straighten out the mess, almost like that teacher who walks into a noisy classroom and puts everyone in their proper place. He proposed that electrons didn't spin around just any way they wanted, but instead occupied well-defined orbits, like steps on a staircase. On that staircase, an electron could only stand on a specific step, never balancing in between. This idea brought order to what once seemed impossible to explain. Think about how public transportation with turnstiles works. You can't stop halfway through the gate, you're either out or you've already passed through. In the same way, an electron couldn't exist in intermediate positions, only in authorized energy levels. Bohr's insight explained the stability of atoms and, on top of that, shed light on the phenomena of energy emission, something that fascinated scientists. And here's where things get even more exciting. By saying that each electron had its own designated place, Bohr opened the door to understanding how light is generated when they switch places. It's as if the electrons were performers on a stage, waiting for the right moment to make the leap that would thrill the audience. But what happens when those leaps occur? The answer takes us straight to one of the most fascinating points in physics: quantum jumps. Quantum jumps are like someone hopping on a staircase. You don't go up half a step, you're either on the lower step or you've already reached the upper one. When an electron absorbs energy, it makes that jump to a higher level. But the magic happens when it comes back down. As it returns, it releases the extra energy in the form of light. That's why we see different colors in fireworks or even in the flames of a stove. If you've ever noticed the bright blue of burning copper salt or the deep red glow of lithium in a lab, you've witnessed quantum jumps in action. Each element has its own light signature, almost like a unique fingerprint in the universe. This even allows scientists to figure out the composition of distant stars simply by analyzing the light that reaches Earth, a true scientific magic happening right before our eyes. And this idea completely changes how we see the invisible. After all, if something as small as an electron can emit light just by changing places, imagine the impact this has on understanding the cosmos. It was this kind of reasoning that paved the way for something even bigger, the foundation of quantum mechanics, a field that would forever reshape modern physics. Bohr's model wasn't just an answer to Rutherford's shortcomings, it was the push science needed to step into a whole new world. By showing that electrons obeyed discrete energy levels, Bohr offered the first practical proof that the universe wasn't a continuous and predictable flow, but rather a puzzle made of tiny building blocks, almost like pixels on a screen. This vision opened the door for other scientists to dare to think beyond the obvious. Einstein had already caused a stir by talking about photons, particles of light, but it was with Bohr's structured model that physics gained a language to connect those pieces. From there, names like Heisenberg and Schrödinger were able to build more sophisticated equations, raising quantum mechanics to the level we know today. In other words, Bohr provided the foundation on which an entire building could be constructed. It's fascinating to realize that everything started with something seemingly simple, electrons jumping between orbits. And yet, from that simplicity came the science that now explains everything from the semiconductors in our smartphones to the lasers that correct vision problems. However, like every discovery, this model wasn't flawless. Cracks began to appear when it was tested on systems more complex than hydrogen. Bohr's model was a revolution, but like every good theory, it also had its Achilles heel. Working perfectly for the hydrogen atom was a victory, but when scientists tried to apply the same reasoning to atoms with more than one electron, everything started to fall apart. The math didn't add up, the results didn't match, and the explanations were no longer as convincing. It was like trying to use a ruler that's too short to measure a bridge. This limit became even clearer when physicists realized that electrons didn't behave as neatly as the model suggested. They weren't just runners in fixed orbits, but dancers on an unpredictable stage, driven by probabilities. And it was precisely this flaw that opened the door to a new interpretation, modern quantum mechanics, with its concept of orbitals and electron clouds, far more complex and realistic. But here's the irony. Bohr's model, even with its flaws, was indispensable. Without it, we wouldn't have taken the next step. It's like that makeshift ladder someone builds to reach the first floor. It won't last forever, but without it, no one would have left the ground. And that's where it becomes clear how every apparent mistake can actually be an invitation to look deeper. If even the smallest building blocks of reality obey invisible rules, could it be that your life is also asking for new energy levels? Bohr's model shows us that even the most unlikely leap can release light, and maybe that's exactly what's missing in your choices. How about starting to identify which levels you need to leave behind and which new steps you should climb? What would you do if you realized that your own limitations are just outdated versions of an old model? And what if the key to changing your story was accepting that it's possible to leap into something greater, even if it feels risky? These questions aren't just theoretical, they're practical invitations to transform your life right now. And before you go, let me challenge you even more. If this content opened your mind to new possibilities, subscribe to the channel, turn on notifications, and keep this journey going with me. After all, every new video is like another quantum leap of knowledge, and you don't want to stay stuck on the previous level, do you?